Hello, everyone. First, I'd like to thank Giovanni and his team for organizing such a interesting virtual conference, hybrid conference probably, and also for the invitation to allow me to present some of our recent work that we started on magnetic Hopfions. So what I'm going to show you in the next 20-25 minutes or so is where we are right now with using advanced X-rays to really study static as well as then in the future dynamic properties of such magnetic Hopfions. Before I begin, I also like to acknowledge the funding agency who really allows me to perform this work. This is the U.S. Department of Energy Office of Science, Basic Energy Science within the Non-Equilibrium Magnetic Materials program. So a quick outline of my presentation today. So first I will show you some results where we used X-ray imaging microscopy tools to look at the static spin texture of magnetic Hopfions. And then in the second part of my presentation, I will show you some yet unpublished, but you can find them in the archive, data on studying the dynamics of these Hopfion textures, which of course we plan to do after COVID allows us to do it also experimentally. So, and also as a way to acknowledge all the people that were involved in this work, these are the two papers that I'm going to present you today, and I highlighted here the three main players. Noah Kent, who used to be a student, is now a postdoc in Colorado. David Raftery is a first-year student who started right away looking at these Hopfions, and then Paul Sutcliffe, who really brought tremendous theoretical support for the static imaging of Hopfions. And David was also the key person to do the simulations on the dynamics of the magnetic Hopfions. And as you can see down there from the list of collaborators, we used a lot of facilities. I'd like to acknowledge the facilities as well as the people involved with this, the foundry particularly making the samples, the ALS and then ALBA for the X-ray microscopy studies. So as a way of introduction, let me just give you a brief historical overview about topological spin textures from my personal point of view. I think what we're seeing is now that we're going from the more two-dimensional systems into fully 3D dimensional systems. And of course, as many of you know, I guess most of you know, and were involved as well, we started probably off with the vortex structures in permeability disks, which had some very interesting spin textures that was fundamentally interesting, but also thought about as potential applications. It's characterized by a circulating spin texture that follows more or less the shape of the disks, and then in the center, because there is, of course, from energetic reasons, there's the polarity, which means the primarily in-plane magnetization pulls out of the plane, gives rise to a vortex structure, vortex core structure in the center, which can go either up or down, pointing up or down. And it's also true that the chirality, which should also be called circularity, the circulating sense of the magnetization in the disk, can go either clockwise or counterclockwise. And a little later on, people started looking into Skyrmions as topological spin textures, which of course are even more interesting than the vortex structures. And they are characterized basically by a so-called topological quantum number, the Skyrmion number, which basically describes the winding from the left end of the Skyrmion all the way down to the right. And so in here, the Skyrmion, you can see it makes a full rotation of magnetization. Now you can even then say, well, the vortex to start with, nobody talked about this, but it's kind of a half rotation. It goes from pointing towards you, towards against you. So it's kind of a half rotation of the magnetization in this spin texture. And then, of course, Skyrmions, and this, you'll hear a lot about this in this meeting and many, many others, is very exciting. And a lot of people looking into this. But what comes really next, I believe, is when we basically recognize that Skyrmions, which in this picture here are shown as a two-dimensional arrangement, in reality, you, for instance, have them in a layer, in a magnetic material layer that has a certain thickness, and this is why people started looking into the three-dimensional extension of Skyrmions. And one of them, for instance, are Skyrmion tubes. Others are boppers, chiral boppers, torons, and other structures. And I would like to focus here today on the so-called chiral Hopfion texture. And this is just kind of a representation of this. What it means is the lines here that are color coded represent the direction of the magnetization pointing in a certain direction. For instance, the red one points in this, let's say, X direction. And when you follow this Hopfion texture, which is shown here schematically, you see that those lines, these iso lines of certain magnetization, basically start twisting around a torus here. So, which means that the rotation is both, I mean, a twisting and a turning. And this is then characterized a little bit by this topological number, the linking number, which is described down here. And as you can see, it's the number of kind of linking that happens, which characterizes the Hopfion kind of rank or so. For instance, one linking of these of a red and a blue kind of isolines is the linking number 1, and here it's like 3 when it does 3 times the linking. Now, these Hopfions are started off with a mathematical concept, but they have been looked at in many other research fields right now. And for instance, there's recent results on showing Hopfions occurring in ferroelectrics. That's the work here shown down here in ferroelectrics, and of course, there's then immediately could be considered to be a connection to multiferroics, which is another interesting class of materials. Then, of course, I mean, Schwalyuk and others have looked into Hopfion textures in fluids and in colloids, chiral ferromagnets as well. This 3-dimensional topological solitons. But I want to point you to one thing: is this is the scale here. This is about on the tens of micrometer. And what we're interested in is really bringing these chiral magnetic Hopfions, the magnetic Hopfions, actually down into a much smaller length scales on the couple of nanometer range. There's also recently an interesting paper from Noam Yao and Joel Moore from Berkeley, where they looked into insulators and they defined the so-called Floquet Hopf insulators. Again, slightly related to this field of Hopfions. So, for us to actually get to the Hopfions, we started off with research on target skyrmions, and I will come to this in a minute. But let me just remind you again, how would such a target skyrmion look like? The skyrmion, as I just described, has basically a winding of, I mean, it makes a 1 full turn. That's how a skyrmion is described, with the winding number again showing up here. And the target skyrmion is kind of an extension of a skyrmion, but with the winding number to be more than just one rotation. And this is where the target skyrmions come into the game here. And what you see now is when you consider such a target skyrmion in a sample that has really some thickness, again, it's a realistic sample, then you can color code the spins that point down, point in a certain direction by a certain color. And this is then what's called the isosurface. For instance, the blue ones here are just those where the spins point into the negative z direction. And that means if you then just kind of carve out those one here, you get these geometrical shapes here. For instance, this kind of a ring structure here. And if you keep doing this and for all various directions, and basically paint these isosurfaces with a certain magnetization direction, you end up with these very complex and intertwined, twisted, linked textures. And this, in the end, I think is also a characteristic of such Hopfions. Now, from a synthesis fabrication point of view, what you can see from those kind of studies, it's the anisotropy on the top and the bottom of the disk that really forces the spins to point in a certain direction. And then what happens if you basically do a simulation now and let the energy minimize, you see how they really just fold into this kind of linked spin textures, where again each color represents a certain direction, certain isosurface direction of the mechanism. Now, again, coming back to the topological invariant, the Hopf charge, again, this is the linking number, and this is just the paper from Bratash, Anna Bratash, and others that also use this here. Again, I showed before, linking number 1 means there's one kind of times, it's the isosurface wind 1 time around each other. Linking number 2 means 2 times, link number 3, and so on and so forth. Again, the description is mathematically shown down here. Oh, now let me go back to how we approach this from an experimental point of view. And again, there was prediction by Paul Sutcliffe and others that target skyrmions, which are these n-pi vortices, again, has been known for many, many years. Alex Bogdanov and Hubert in 1999 already had a paper where they talked about this n-pi vortices. And it really came back to our conservation, among others, skyrmionians. People talk about skyrmioniums where you have only kind of 2 rotations. But we actually try to fabricate those target skyrmions and just be able to prove that they're really target skyrmions that we can fabricate. Because, as I said, the theory papers were out there that predicted once you have target skyrmions, you can use them as precursors for Hopfions. And this is how we approach the target skyrmions now, almost 2 or 3 years back. We combined basically 2 systems. One was multi-layer iridium called platinum, certain repeats that we know had a strong BMI, Charles-Marie interaction, also a perpendicular magnetic anisotropy, and they were put on top of those by nanofabrication well-known permalloy discs. And we were just interested what happens underneath those discs, how does actually the imprinting happens of the spin textures in those magnetic films. And on the right column here, you see the results from that study back then, where we used full-field magnetic X-ray microscopy, in particular the penetration power and the elemental specificity, to look through the permalloy discs onto into the cobalt component of this cobalt platinum iridium multi-layer disc. And what we found were spin textures, and I just want to draw your attention to the full circle, so not the broken ones. And you see there's one white black circle here. This is what means the magnetization is pointing one, makes one rotation. This is the regular skyrmion. And then you see 1, 2 of them, 2 pi rotation here, 3 pi rotation, and underneath this about 400, 500 nanometer disk structures up to about a micrometer. We were able to observe up to 4 of those rotations, and this is what we then demonstrated or showed, that these are really target skyrmions up to a 4 pi rotation. So from that point, from that research, we knew we were able to fabricate target skyrmions, and this was of course then the next step. So how do we bring them into Hopfion texture? And here's now kind of schematics that shows you how do target skyrmions on the left and Hopfions on the right schematically basically how are they different from each other. And when you just follow this color-coded kind of arrows here, you see, for instance, that the target skyrmion across the thickness of the disk is more or less the same. So it doesn't matter whether you do a kind of a depth-dependent imaging of a target skyrmion, you should more or less see the same thing. Now this is the huge difference to the Hopfion, as you can see here. Here you have this kind of twisted torus structure in the center, and as you can see, there's a clear, very pronounced difference for the first couple of layers up here, or the first couple of nanometers of the spin texture between the Hopfion and the target skyrmion here. And this was something that we said, well, we have various X-ray microscopies, magnetic X-ray microscopies, that should allow us to probe either the surface region here or go all the way through, and then just combine those 2 images and compare them, and we should be able to distinguish the Hopfion from the target skyrmion. This is what we've done. So we used basically the 2 well-known techniques, X-ray 4-emission electron microscopy shown on the right here, which, as you probably all know, is very surface sensitive because it detects the electrons that escape a certain surface depth and then are being accelerated through an electron optics onto the CCD camera, where you generate, due to the XMCD signal, X-ray magnetic circle dichroism signal, the spin texture in this surface region. And then we have full-field transmission X-ray microscopy, which is also full-field like the PEAM, but you will go all the way through the sample and you just see the kind of bulk average signal XMCD. And we made a sample that we could stick in both of these instruments, and we labeled them. We know exactly this that we're looking at is exactly the same that we looked at with the PEAM and with the full-field microscope. Spatial resolution, we didn't push it to the limits, but it was more or less the same. So that means even when you then compare those two images, should be around same, about 30 nanometer spatial resolution for the roughly 1 micrometer disk size. Definitely, this is a feasible experiment. So we used the specific surface sensitivity versus bulk sensitivity, combined them into two, and basically looked at. So let me go back briefly one more time. We designed then these Hopfion systems following the theoretical predictional simulations in such a way that we designed the PMA profile across the thickness of the multilayers. And what you see here are, again, simulations that we did together with Paul Sutcliffe. And for the target Skyrmions, you see again that there's a more or less uniform kind of spin texture across the thickness. Whereas if you vary the PMA profile that's shown down here in the center and the bottom one, you're able to really push the spin texture into a Hopfion structure. So this is a schematic how we actually synthesize the samples, these multi-layers, and what you can see is the target Skyrmion up here had a uniform cobalt layer thickness percentage in between the platinum and the cobalt. But the difference for the Hopfion is that we designed and we basically tailored the PMA profile across the thickness by reducing the thickness of cobalt in the top and the bottom layer here. And by doing so, we were quite confident that this should allow us to create Hopfions in these multi-layer structures. And then we did one more simulations just to understand a little better what to expect when we now engage with these PEAM and the MTXM microscopy tools. And the top here you see a simulated experimental image of a PEAM for the target Skyrmion, as well as the same for the MTXM. And what you can see here is that the structure that you would observe with the PEAM and the MTXM is not different, which again is not surprising because the spin texture looks more or less the same throughout the whole multi-layer thickness. So again, you have this black kind of center, both in the PEAM and the MTXM, surrounded by a kind of a brighter white ring. But the significant difference comes when you have a Hopfion and you look with the PEAM on the surface near region, and this is shown here as a simulation. This is how a single image for a specific direction of the K vector of the photons pointing onto the spin texture, we would expect that we would see no longer this kind of target Skyrmion pattern, but we would see something like a black and white, almost yin-yang like spin texture. And of course, if you would then rotate the sample, that means we change the relative orientation between the K vector and the spin texture in the surface near region. This should allow us to really retrieve and reconstruct a fully three-dimensional spin texture in the surface near layer. Again, for the MTXM, as I said earlier, the target Skyrmion and the Hopfion does not look any different because apart from this changes on the closed surface near region, it looks more or less the same throughout the whole bulk of the material. So black center surrounded by a bright ring here, as both for the top target Skyrmion and for the Hopfion. And now here are real experimental data. On the left, again, this is what I just described, the full D reconstruction from the expected simulations for the PEAM. And here in the center now are PEAM data. And what you can nicely see is how these black and white structures are showing up depending on the relative orientation of the K vector of the X-rays to the sample orientation. That means we rotated the sample. So you can see, for instance, this black and white goes from pointing to the left, pointing up and down. And those data were then used to combine into a full 3D representation shown here of the surface near region. And this is very close. It has the same features that we would expect from a Hopfion texture. For comparison, again, the MTXM, as expected, looked both in the simulation as well as in the experiment. But as I said before, the MTXM alone cannot distinguish a Hopfion from other from particular target skyrmion. And so to be clear that we were really seeing and confirm that we really saw a Hopfion texture, we compared again different three-dimensional spin textures to our experimental data, and here's just 3 of them: target skyrmion, as I mentioned many times before, the Hopfion here in the center, and also Toron. And it's pretty obvious that the surface near region that can be viewed with the beam in the target skyrmion, Hopfion, and the Toron looks vastly different. And even for the Toron, MTXM would look different compared to Hopfion or a target skyrmion. So conclusion is, we not only designed following theoretical predictions the Hopfion containing multi-layer structures, we also were able to get evidence and confirmation that the images we found both in the beam and the TXM are consistent with the identification of a Hopfion. So now let me come to the second part briefly, and this is about the dynamics. So we've just shown that we can design Hopfion multilayer containing structures, and we were able to image the static ones, but there is a lot of interest now looking into Hopfion dynamics. Why is it interesting? Let me just compare briefly what is different between skyrmion dynamics and Hopfion dynamics. As you probably all know, in skyrmions there is the so-called Skyrmion Hall effect, which in the end means the skyrmion following on a racetrack would be deflected because there is a gyro vector. And this is of course a very unwanted side effect. I know a lot of people are trying to find mechanisms, processes, strategies to basically balance it back so they can go on a racetrack straight along. But the Hopfion has a fundamental difference compared to a skyrmion, and that means it has no zero net gyro vector. And with that, and this was pointed out, for instance, in these papers down here about the Braters, there is no deflection. And so it's basically a compensation, an inherent compensation of this kind of Skyrmion Hall effect given by the spin texture of the Hopfion. So I just want to highlight here a little bit the work by Xiaodong, which is really beautiful. And what you see here is, and again, this is simulations. This is not experimental data yet. The Hopfion will do some, when you basically excited by the spin torque dynamics. The spin torque dynamics, you have kind of tumbling and rotating kind of dynamics that's going on. So it's a very complex dynamics that's going on. But again, this is, I think, pretty challenging and pretty attractive to try to do this with experiments like we did with the vortices, starting with the vortices like we did with, and many others with Skyrmion dynamics. It's just a natural step forward to also do the Hopfion dynamics. Now let me just briefly sum up a little bit what would be characteristic important structures in such a Hopfion. And I just want to point here, and this is again all simulations, there is the so-called vortices, and they are located actually at the maximum of vorticity. These are very characteristic for such a Hopfion, and you're probably familiar with the work by Claire Donnelly and others, who started looking into the so-called vortex rings in a gadolinium cobalt-2 material. They were able to identify by this study here that they've seen this kind of vortex rings in the bulk magnet. So this is something similar that we would like to again see and study the dynamics of these Hopfions with the vortex vortices that are happening on the top and the bottom of the. Now, what happens if you apply a magnetic field in z direction to the Hopfion? Simulations show that it would basically transform into a so-called Toron. Now, the Toron would have then not only these vortex rings or the vortices, but the Bloch points. And also Bloch points, as you probably all know, are a subject of high interest. And here's just one paper I want to highlight here by Aurelio and others, Herrera Rodriguez, where again they used soft X-ray tomography to study these magnetic singularities and topological charges. Actually, they were able to look into a Bloch point with soft X-ray data. And again, this is something that we would like to take advantage of and now study the dynamics. The probably most remarkable feature that we found in our simulations was what happens to the Hopfion structure when you increase the applied magnetic field. And what you see here is plotting the total exchange energy as a function of the applied magnetic field. And in blue, see the Hopfion kind of ground state, and then in red, the Toron ground state. And what you see is that at about 65 or so millitesla applied magnetic field, the Hopfion state transforms or collapses into a Toron state. This is also shown here in this kind of movie. And what you were able to see is how the Hopfion texture, this kind of linked isosurfaces, collapses finally into now this one here, which is the Toron state. Again, these are now all simulations that are just waiting for experimental verification. Okay, and then we started to play a little bit with the dynamics. So we had, of course, the field, and we looked into the spin wave resonances here. And I just want to point you to basically the summary slide here. I mean, we did a sync function here. You can see very nicely some bands as of course, functional frequency. And again, here at this 60, 64 so millitesla, there's this transformation from the Hopfion on this side to the Toron. So again, if you think about doing experiments with these multi-layers with Hopfions and you apply a magnetic field, we predict that you should see very interesting, strong spin wave resonances as a function of magnetic field, and then they will have drastic kind of drops, changes when you go from the Hopfion state to the Toron state. We also plotted a little bit these different resonance frequencies and how would they look like in kind of a graphical interpretation. As you can see them here, this is the amplitude, blue is the minimum, red is the maximum, and as you can see, they correspond to this is at 50 millitesla in the Hopfion state, this is at 80 millitesla at the Toron state, and you see these kind of numbered resonances, H1 up to H8, we plotted here, and you can really see how they form different actually amplitudes at certain locations in the structure. And this is of course very different for the Toron and the Hopfion here. But again, the key here will be to understand how these vortices and the block points behave. And these are again studies that are coming up as soon as COVID will allow us to do this. Okay, with this, let me summarize my talk. I hope I could show you that Hopfions are really exciting topological nanomagnetic objects. They do have a very characteristic 3D spin texture. Our approach was to start from target skyrmions, use them as precursors in tailored multi-layer systems, and then we used signature properties of PEAM and MTXM to observe the static spin textures. The dynamics of Hopfion textures can be excited by many means, but they also show characteristic features. The macromagnetic simulation so far that we have seen indicates characteristic frequency bands, which are, as I just said, associated with vortices and block points. With this, I'd like to thank